Right, next round of identities that we're going to learn are called composite identities. So there are composite identities, sometimes called sum difference identities for sine and cosine. And here's your rules for cosine. So we like to say cosine is selfish. It wants to go first. Also note that the signs are opposite. So when we add inside, we subtract outside. That's fun. And when we subtract inside, we add outside. So cosine, cosine minus sine, sine. Cosine likes to pair with itself. All right, example 1, find the exact value of cosine of 15 degrees. So what these identities can allow us to do is to find the exact values of trig functions in either multiples of 15 degrees or multiples of pi 12ths if we're in radians. So what I want to do is find two unit circle angles that are either add to 15. Well, we can't go smaller. The smallest one on the unit circle is 30 besides 0. So I need two angles that subtract to give me 15. So those angles, keep it simple. I'm going to go with 45 and 30. So cosine of 15 degrees is equivalent to cosine of 45 degrees minus 30 degrees. That's still 15, but I'm going to go so I can use that composite for cosine. So this is your difference. So cosine it pairs with itself, so it's going to be cosine 45 times cosine 30. Opposite operation, so since we subtracted, we're going to add, and then sine 45 sine 30. All right, cosine of 45, I struggle with the degrees, I'm more of a radian person, is 45 degrees is our pi fourth, so cosine of pi fourth is square root of 2 over 2. Times cosine of 30, 30 is our pi 6, so the x value there is square root of 3 over 2. Plus, and then sine 45, also root 2 over 2. Yeah, you thought you were done with that unit circle, but you're not. And then sine of 30 is the y value at that pi 6, 1/2. All right, top times top, bottom times bottom. Two square roots multiplied, we can multiply the numbers underneath. Square root of 6 over 4 plus root 2 over 4. Denominator is already mapped, so no work to do there. Just combine root 6 plus root 2 all over 4. All right, next up, composites for sine. So notice you can use any letters to represent angles. I'm going to throw some Greek letters in here, alpha and beta. So sine isn't selfish like cosine. Cosine has to pair with itself because it's selfish. Sine likes to share, so it alternates. So it's sine, cosine, and then you swap the angles, cosine, sine. Also note the sign does change in between. The sign does not change in between. Sine, keep the sign. So plus stays plus and minus keeps minus. So sine shares and sine keeps the sign. All right. Exact simplified value of 35 pi 12. So we used subtraction last time, so let's try to use addition this time. All right, so I need two unit circle angles that add to 35 12. So let's try to break this up and see what we can come up with. Let's go with, so it's got to be divisible by 12. So if we go with, let's see, 10 and let's see this, 25 over 12. 25 over 12 is not going to help us, so let's see, 10 does. Let's try 9. Let's try 9 and 26. Let's see if we can do that. So I'm going to do 9 pi 12ths plus 26 pi 12. So before we break this up, let's go ahead and reduce them, double check that they are on the unit circle. Because if you use two angles that are not on the unit circle, you're going to go in circles. It's not going to work. I meant to write my sine 35 pi 12ths here. All right, 9 pi 12ths. If we do 9 over 12 and reduce our fraction, we want to make sure it's unit circle. That is going to be 3 pi 4ths. So we win with the first one. If we go to the second one and do 26 over 12 and double check that it is unit circle, we're going to get 13 pi 6. So while it doesn't seem like it's unit circle, it is just over rotated. But any multiple of pi 6 is on the unit circle, so we're safe. All right, sine shares. So sine 3 pi 4th, cosine 13 pi 6, same sign, sine keeps the sign, plus now it goes cosine 3 pi 4 sine 13 pi 6. All right, we can do the 3 pi 4 without a problem, but the 13 pi 6, just quick review, coterminal angles, everything's tying together. 13 pi 6, if we get rid of a rotation, so if we get rid of one full rotation, 2 pi, that is going to leave us with pi 6. So they're coterminal, so that means their sine and cosine values are the exact same. So when we do sine of 13 pi 6, we just think about it in terms of sine of pi 6. All right, sine of 3 pi 4, 1, 3, that's in quadrant 2. Sine is positive, so square root of 2 over 2. Cosine 13 pi 6 is going to be the same as cosine of pi 6, square root of 3 over 2. Cosine 3 pi 4 is in quadrant 2, so it's negative, square root of 2 over 2. And then sine 13 pi 6, same as sine of pi 6, 1/2. All right, top, top, bottom, bottom. Root 6 over 4 plus a negative root 2 over 4. They match already, so just slide them together. So root 6 minus root 2 all over 4. All right, we can also use those composites backwards. So if we're given the expansion, we can condense it back down using either the sine or the cosine. So you got to decide whether it's the composite with sine or a composite with cosine first. So if I look at this one, I know sine likes to share. So because we're alternating, I know this is a composite with sine. So sine keeps the sine, 22 degrees plus 38 degrees. 22 plus 38 is 60. I'm not very good with the degrees. I like my radians. Sine is 60. That is the same as pi thirds. The sine value of pi thirds is square root of 3 over 2. So we can use those composites backwards. All right, tangent. Tangent is a little more complicated. We also have a sum and a difference for tangent. So tangent, you could use composite for, because tangent is sine over cosine, you could use a composite for sine in the numerator and then the composite for cosine in the denominator, but that is going to be far more complicated to simplify. So this is your best bet. So you hold the sign in the top, you change the sign in the bottom. So notice the numerator signs are the same. The denominator is the opposite sign. So it's keep the sign on top, change the sign on the bottom. Same for the subtraction versus addition. So sum, keep the sign, difference, change the sign, multiply at the back. Tan plus tan, 1 minus tan times tan. All right, tangent of 17 pi 12. So I need two unit circle angles that either add to 17 or subtract to 17. So tan 17 pi 12. I would be thinking adding might be the best option. Let's see. All right, so let's see if we can come up with two that add. So tangent of, well, let's see, 17 would be a 15 and a 2. So let's try 15 pi 12 and a 2 pi 12. All right, reduce first. So if we do our 15 divided by 12, that gives us 5 pi 4ths. So we're good. That's on the unit circle. And then if we do our 2 pi 12ths, it's going to give us pi 6. So yes, both on the unit circle. All right, composite for tangent. Tan, keep the sign. First, plus tan of the second. Denominator, 1, opposite operation. So 1 minus, and then it's multiply. Tangent 5 pi 4 times tangent pi 6. Like I said, you can do it with sines and cosines. So you have composite for sine on the numerator and then the composite for cosine on the denominator. It's just a lot. This is easier. All right, 5 pi fourths. That's in quadrant 3. Oops. In quadrant 3, tangent is positive because it's negative and negative. So that is a 1. Tangent of pi 6. I got to go off to the side for this. So tangent of pi 6. Here's our pi 6 angle. X, square root of 3 over 2. Y 1/2. So if we do y over x, that is 1 over square root of 3. But we've got to rationalize it. So that would be square root of 3 over 3. It's bothering me. It's not in the middle. So yes, all that rationalizing still in there. All right, so then we have 1 minus, and then it's the same values. 5 pi 4 is still 1. Pi 6 is still square root of 3 over 3. All right, the 1's pointless, so let's go ahead and rewrite. 1 plus square root of 3 over 3 over 1 minus root 3 over 3. All right, so we have an answer, but we do not have a proper answer. It's not rationalized nor simplified because it's got complex fractions. So some of those strategies we used with those identities we're going to use here. So first thing I want to do is clear the 3, then I'll worry about the square root. So I need to clear that little baby denominator of a 3. So we're going to multiply by 3 over 3. That 3 is going to the 1 and to this fraction here. So that's going to give us 3 times 1 is 3 plus 3 times a fraction is just the square root of 3. For the denominator, same thing. It's just going to have a minus in the middle. So whoops. So we're going to go here, just right on top of everything. Okay, one more try. Here. Okay, we'll do that one. And here. There it goes. Okay. So that's going to be 3 minus square root of 3. So clear the baby fractions first. Then we can rationalize. So this is your conjugate rationalization. It's been a while. It was way back in college algebra. So another form of 1. This is your conjugate form of 1. Keep the real part. Change the sign on the irrational part. So goal is to get the square root out of the denominator. So we're going to change the sign on the square root in the denominator. So that gives us, we have 3 plus square root of 3 times 3 plus square root of 3. Notice it's the same thing, so we'll probably write it as 3 plus square root of 3 squared. And then over, we have 3 minus root 3, 3 plus root 3. So now we need to get this thing multiplied out. And we'll start on the bottom. Go sideways for a minute. So FOIL on the denominator, 3 times 3, 9. Its difference of squares, outside, inside drops. So last, positive times negative, negative, square root of 3 squared, 3. All right, for our numerator, I'm just going to rewrite it as 3 plus square root of 3 quantity squared for now. All right, I need to make some room, so we're going to come over here. Put a little bar to show the separation. And we're going up here. Next, so that is 6. So I'm going to slide it out front as a 1 over 6. All right, it's going to depend on the format of the answer. I don't really have a problem with this kind of answer. And you may have to multiply it out. Again, just it's going to be personal preference. Also, it's going to depend on the directions for the problem. So if you are asked to multiply it out, we'll go ahead and do that. So you're, again, thinking FOIL. If you want to write them side by side, you can. That's going to give you 3 times 3, 9, plus 3 square root of 3, plus another one. So that's going to be 6 square root of 3. And then last, square root of 3 squared, 3. All right, we still got our 1 over 6 floating. 9 and 3 is 12. So we get here, distribute your 1 over 6. 12 times 1 over 6 is 2. 6 and 1 over 6, 1. So that's mostly how you're going to have to enter the answer. So be careful with your multiplication. All right, just like sine and cosine composites can be used backwards, so can the tangents. Okay? So the key is you're using the sign that is on the top, because the numerator, sine keeps the sign, and remember, sine came from the top. Cosine switches the sign, and for tangent, cosine's in the bottom. So that's one way to kind of think about getting those signs correct as well. So this is going to be tangent of pi fifth plus, because we're keeping the sign on the top, 4 pi fifth. And 4 plus 1 is 5. Tangent of 5 pi fifths is tangent of pi. I don't need the parentheses. Tangent of pi, ratio of y to x at the angle pi, is 0. All right, composites can also be used in verification of identities or in verification of proofs. So, verifying identities or proving statements, a red flag you need to look for is that your angles must be the same. So if I am looking at this identity here, the left side angle is not just x, but the right side is. So I need to go to the left and I need to use a composite identity to get those angles down to just x. So we're going to use a composite for tangent on the left. So for tangent, it is tan, first angle, keep the sign, tan, second angle, over 1, change the sign, so minus tan times tan. So tan x times tan pi 4. All right, tan of pi 4 is 1, so that's tan of x plus 1. Tan of pi 4 on the bottom is also 1, so 1 minus tan x times 1. So if I look, numerator's backwards on the other side, so let's swap it. So 1 plus tangent of x, a plus b, b plus a, doesn't matter. And then 1 minus tan x. Next one. All right, once again, if your angles don't match, work on the side with the more complicated angles. So looking at this one, that's clearly the left side. So we got two composites here, one with a sum and one with a difference. All right, so we'll need a lot of room. So sine of x minus y. Sine likes to share. Sine, first angle, cosine, second angle. Sine keeps the sign. Cosine, first angle. Sine, second angle. So there's my composite for sines subtraction. Plus, now I'm going to go use the composite on this second one, the sine of x plus y. So sine shares. Sine x, cosine y, keep the sign. So we're going to keep the plus sign. And then it is cosine, swap the angles, x, sine y. All right, so if we look at this, I have a cosine y sine x and a cosine y sine x. 1 plus 1 is 2 of them, so I have 2 sine x cosine y's. If I look at the other two, a negative cosine x sine y plus a positive cosine x sine y, that's 0, so those are gone. And if we look, let's see. Did we get our... Oh, that's a typo on my part. I'll fix it on your paper. Oops, that's supposed to be a Y. Your copy will have that adjusted. So here's the magic. I'll fix it here. That's supposed to be a Y. There we go. If only they were all that easy, right? Yeah, that's my bad. It will be fixed on your paper. All right. Next one. Again, there was the tip I just gave you. Make sure your angles match. If your angles do not match, you need to go to the side with the more complicated angle and start there. So if I look at this one, left side, the angle is 3x. That's not going to work. I need an angle all the way down to x. So goal is to get this down to just a singular x. So we can focus on a sum. I would not focus on a difference because that usually requires making an angle bigger. So I am going to break this into the left side. Sine of 2x plus x. So sine shares, so that is going to be sine of the first angle times cosine of the second angle, keeps the plus sign, cosine of the first angle, sine of the second angle. So then we look at this again, I'm still not there. So now what we got to do is we got to work on this. So sine of 2x, what we're thinking is we're going to do this with x plus x. So I'm just going to write that x plus x right there. All right, so sine first angle, x, cosine second angle, which also is x, plus cosine second angle, sine first angle. Okay. All right, so I'll leave that in pink. And then that cosine that's next to that box, that cosine is still sitting here. All right, so then we're going to scoochie because we got to do something else again. All right, so now we're going to go, I want my purple back. There it is. Here. So now I got to work on this, which is also x plus x, but it is with cosine. All right, so if we go with that, cosine, first angle, cosine, second angle, opposite operation, sine, first, sine, second. And then that sign next to that box, still there. So we're here. Okay, so sometimes different colors can help keep you organized. All right, before I even try to deal with what's attached to those parentheses, I want to focus on the inside because I can rewrite it a little bit better. That is sine x cosine x plus cosine x sine x. A times b, b times a. It doesn't matter. Those are like terms. That is 2 cosine x sine x. And then the cosine's still out here. We haven't done anything with it yet. And then plus, if I look at the inside, well, cosine times cosine, that's cosine squared. And then sine times sine, that's sine squared. So we get here. All right, next thing I would do, distribute, get our multiplication done. So this one, first one right here is just multiplying. There's no separate terms, so that's going to be 2 cosine squared of x times sine of x plus this second one we do need to distribute that sine, so it's going to be cosine squared x sine x minus sine squared times sine, which is going to be sine cubed. So then if we look, those first two are actually like terms. So I have 2 is something plus 1 is something. That's 3 somethings. So I have 3 cosine squared x sine x minus sine cubed of x. Let's see. That's it. All right. Next. All right, left versus right, looking at that right side, the angles don't match. So we're going x plus x. All right, so cosine is selfish. So cosine first angle, cosine second angle, they just happen to be the same. Change of sign, sine first angle, sine second angle. Look at that. Cosine times cosine, cosine squared. Sine times sine, sine squared. Done. This right here is actually called a double angle identity. Double angle identities are covered in the next section. So this is a new identity you will get in the next section. And remember, you can actually just use the composite. Next one. Sine 2x. Same process, 2x is x plus x. So sine shares, sine first angle times cosine second angle. Keep the sine, cosine first angle, sine second angle. Those are like terms, just the multiplications backwards. So that is going to be 2 of them. 2 sine x, cosine x. This is your double angle for sine. So you will actually get these as identities that you can use in the next section. I don't like to memorize those identities because it can be done with a composite just like we did here. All right, so that's the end. Be very careful with your algebra on those proofs as you're going through it.